You've heard that sound your entire life, that rhythmic, clicking, clunking. Every time you ride a train, most people find it relaxing. Some people fall asleep to it. But almost nobody ever asks, why is that sound even there? Because here's what's actually happening every time you hear that click. Your train, which can weigh anywhere between 400 and 10,000 tons, is crossing a gap. A gap that engineers put there deliberately. And if those gaps didn't exist, if someone removed them, welded everything shut, decided they weren't necessary, the rail would eventually bend itself apart under enormous internal pressure. That's not a theory. That's not a worst-case scenario. It has happened repeatedly, in multiple countries, in living memory. So today we're going inside the physics, the engineering, and the history of one tiny gap that the entire global railway system depends on. Let's go first. Let's be clear about what we're actually looking at. Those gaps between railway tracks are called expansion joints. And they exist because railway track is not one continuous piece of steel stretching for hundreds of miles. It's built in sections, individual lengths of steel, typically between 12 and 25 meters long, laid end to end across the ground, with a small deliberate space between each one. In older railway systems, the ones built in the 1800s and early 1900s, those gaps were obvious, audible, rhythmic. That's where the classic sound comes from. Mickety-clack, clickety-clack, one click per gap, one gap per section. On a long journey, thousands of them. Now here's the obvious question. Why not just eliminate the gaps completely? Connect everything. Weld every section together. Smoother ride. Quieter journey. Simpler engineering. It sounds logical, but it ignores something that every piece of metal on this planet does without exception. Something that turns a simple engineering decision into a matter of life and death. Here is a fact that sounds simple but has consequences that are genuinely enormous. Metal expands when it gets hot and contracts when it gets cold. Every metal, every alloy, every steel rail, everywhere on Earth. No exceptions. When temperature rises, the molecules inside the metal vibrate faster, push harder against each other, and the entire object physically grows larger. When temperature drops, the opposite. Molecules slow, pull closer together, and the metal physically shrinks. Now this sounds like something that barely matters in real life. A little bigger, a little smaller. So what? Here's why it matters enormously. A standard steel rail, just 25 meters long, expands by approximately 7.5 millimeters for every 10 degrees Celsius of temperature rise. That sounds tiny. Let's scale it up. A typical railway line between two major cities, say 500 kilometers long. That's 20,000 individual rail sections. A temperature swing of 30 degrees Celsius, completely normal between a cold morning and a hot summer afternoon. Each section wants to grow by roughly 22 millimeters. Multiply that across 20,000 sections, 0.440 meters. The entire track wants to physically grow by nearly half a kilometer, and it has nowhere to go. Here's a simple way to understand the force that creates. Imagine placing a soda can between two rail ends with no gap between them. As the temperature rises and the rails try to expand, the can doesn't dent. It doesn't bend slowly. It gets crushed, completely flat before the rails have even fully touched each other. That's the force building inside a rail with no room to expand. Now multiply that across 20 sections pushing simultaneously in the same direction. The compressive force of a fully loaded rail in peak summer heat is equivalent to over 500 tons pressing sideways against the gravel, holding the track in place. The track isn't just under pressure, it's under the equivalent of a 500-ton weight pushing sideways, and the only thing stopping it from moving is gravel. So what does steel do when it can't expand? It doesn't stop. It doesn't wait. It pushes. The pressure builds inside the rail like a compressed spring with no release. And when that pressure exceeds what the rail can hold, the track buckles. It doesn't crack. It doesn't crumble. It physically bends sideways like a ruler being pushed from both ends. And when that happens under a 400 train traveling at 120 kilometers per hour, there is no good outcome. This isn't theoretical. Track buckling from thermal expansion has caused real derailments, real injuries, real deaths. And it keeps happening. Maryland, USA, July 2002. A MARC commuter train derailed after track buckled due to extreme heat. Multiple passengers were injured. The National Transportation Safety Board confirmed thermal expansion as the primary cause. Washington, D.C. metro area summer incidents. The Washington metro system has documented multiple cases of track buckling during summer heatwaves, forcing emergency speed restrictions across entire lines. United Kingdom, July 2022. This one made global headlines. The UK recorded temperatures above 40 degrees Celsius for the first time in recorded history. Railway operators immediately issued emergency speed restrictions across the entire national network. Not as a precaution, as a necessity. Dozens of services were cancelled. Hundreds of thousands of passengers were stranded. Multiple sections of track were inspected and found to be dangerously close to buckling. And railway engineers publicly stated the tracks were not designed for those temperatures. They were built based on historical climate data. Data that is now being exceeded regularly. Australia, multiple incidents. Multiple years. Australia's railway networks deal with thermal buckling more than almost any other country due to extreme inland temperatures. In South Australia and Western Australia, summer temperatures regularly exceed 45 degrees Celsius. Rail operators use dedicated track monitoring vehicles that run overnight specifically to check for buckling before morning services begin. In 2019, a freight train derailed in South Australia following track buckle caused by extreme heat. No fatalities, but significant infrastructure damage and months of repair work. This is not ancient history. This is not a solved problem. Every summer in every country with a significant railway network, engineers are managing the same fundamental threat that has always existed. Metal, heat, nowhere to go. And the tiny gap that most passengers have never once thought about is the primary defense against it. So now we know why the gaps exist. But here's where most people just assume it's simple: just leave a space. Problem solved. It's not simple at all. The gaps are engineered with extreme precision. And every component is designed around one goal: allow controlled movement, while keeping the track perfectly aligned. Because if the alignment fails, a wheel that's supposed to roll smoothly across a joint instead hits a misaligned edge at full speed. At 120 kilometers per hour, that's a catastrophic impact force hitting a steel wheel the size of a dining table. So here's how they solve it. First, the rail ends are cut at a slight angle, not straight across. If the ends were perpendicular, when they expand and meet, they'd slam together flat, creating massive impact concentrated at one point. With angled cuts, the rails slide against each other slightly as they close, distributing the force across a larger surface area. Second, fish plates. These are heavy steel bars bolted to the sides of both rail ends, holding them in precise alignment while still allowing forward and backward movement. Think of it like a sliding drawer. It stays in the frame. It stays aligned, but it can move. Now here's the critical part most people miss. If those fish plate bolts loosen over time from vibration, from weather, from thousands of heavy trains crossing daily, the joint starts to shift, not collapse, not fail completely, just shift. By millimeters, but on a railway track, millimeters matter enormously. A rail that shifts out of alignment by just 5 to 6 millimeters at a joint can cause a wheel flange to climb the rail, the first stage of a derailment. This is why railway maintenance crews physically walk track sections and check every single fish plate bolt by hand. This is why track inspection is one of the most labor-intensive jobs in the entire transportation industry. The gap keeps the track from buckling, the fish plate keeps the gap from becoming a trap, and the maintenance crew keeps the fish plate doing its job. Remove any one layer and the whole system is compromised. Third, the size of the gap is not guessed. It's calculated. Engineers determine the precise gap size based on the installation temperature, the expected maximum summer temperature for that region, the minimum winter temperature, and the specific alloy of steel being used. In Canada, where temperature swings between -40 in winter and +35 in summer are normal, the gap calculations are extremely complex. The gap must be wide enough that summer heat never closes it completely, but narrow enough that winter cold never widens it so far that the fish plates crack under the pulling force. Both failure modes are real. Both have caused incidents, and the gap is the single variable that controls both outcomes simultaneously. Now here's where this story gets a genuine twist. Because if you've ridden a modern high-speed train, the Shinkansen in Japan, the TGV in France, high-speed rail in China, you may have noticed something. No clicking, no clunking climate silence. So did they solve it? Did engineers finally figure out how to eliminate the gap completely? Sort of. And the sort of is the interesting part. The technology is called continuously welded rail, or CWR. Instead of laying sections with gaps, engineers weld them end-to-end into continuous lengths, sometimes stretching 400 meters or more without a single joint. Smoother, quicker, faster, safer for wheels and axles. But the physics didn't change. Steel still expands in summer. Steel still contracts in winter. The expansion force is still there every single day. The difference is in continuously welded rail. That force has nowhere to go longitudinally. The welds are stronger than the expansion force. The rail cannot grow longer, so instead the force converts into internal compressive stresses inside the steel itself. The rail is essentially under permanent internal pressure. Invisible, silent, and if it exceeds safe limits, just as dangerous as before, because continuously welded rail can buckle too. And when it buckles, there was no clicking to warn you, no visible gap to inspect. No obvious sign that anything was wrong. The failure arrives without announcement. This is why high-speed rail networks invest enormous resources in track stress monitoring. Sensors embedded in the track measuring internal stress in real time. Infrared cameras on inspection trains measuring rail temperature across entire networks overnight. Automated systems that flag any section approaching dangerous stress levels before morning services begin. And it's why even on the world's most advanced high-speed networks, when a serious heat wave hits, you hear announcements like, due to high temperatures, all services are operating at reduced speed. Not a precaution. Miscs, at reduced speed, even if the track develops a slight buckle, a train has a chance of surviving it. At 300 kilometers per hour, that chance approaches zero. The gap wasn't eliminated by continuously welded rail. The gap was internalized, made invisible, and in some ways made more dangerous because now you can't see it. Before we get to why all of this matters more today than it ever has before, here are two details about railway tracks that almost nobody knows. One, the rails are deliberately tilted inward. If you look carefully at railway tracks, the rails are not perfectly vertical. They're angled slightly inward, about 1 in 20 on standard lines. Why? Train wheels are not cylindrical. They're slightly conical, wider on the inside, narrower on the outside. When a train goes around a curve, the outer wheel needs to travel further than the inner wheel. The conical shape automatically compensates the outer wheel rides on a slightly larger diameter and naturally covers more distance per revolution without any steering mechanism, without any computer, using pure geometry. This was figured out in the 1830s. It still works the same way on every railway on Earth today. Derailed too, not all tracks are the same width. The distance between the two rails, called the gauge, is not universal. Most of the world uses 1,435 mm standard gauge, originally based on the width of horse-drawn wagon wheels in 1800s England, but Russia uses a wider gauge. Spain's older network uses a different width entirely. At border crossings between mismatched systems, trains stop and have their wheel bogies physically swapped underneath before continuing. It sounds like a pure inconvenience. But during wartime, it was intentional defense. An invading army that captured your railway network couldn't use it if their trains didn't fit the tracks. A measurement difference of a few centimeters. A strategic advantage that shaped the outcome of wars. Here's the part of this story that most people don't hear. Climate change is not just an environmental problem. It is an infrastructure problem. Railway tracks built in the 1950s, 60s, and 70s were engineered using historical temperature data from those decades, the expansion calculations, the gap sizes, the continuously welded rail neutral temperatures, all based on a climate that no longer exists. The temperatures being recorded today in Europe, North America, and Australia are regularly exceeding what those tracks were designed to handle. The UK's 40-degree heatwave in 2022 was not supposed to happen for another 50 years. According to 1980s climate models, it happened. And railway engineers across the world are now doing something they've never had to do before, retroactively recalculating the thermal limits of infrastructure that was never built for these temperatures. New rail alloys with higher thermal stability are being developed and tested in labs right now. And the neutral temperature calculations for continuously welded rail, the invisible internal stress balance we talked about earlier, are being completely recalibrated for a hotter future. The tiny gap that billions of passengers have crossed without a second thought is now at the center of an engineering rethink happening on every major railway network on Earth simultaneously. Because the margin between a safe journey and a catastrophic one is measured in millimeters. And those millimeters are shrinking. Next time you're on a train and you hear that sound, you'll know what's actually happening. Engineers calculated the exact temperature range of that region, measured the exact expansion coefficient of that specific steel alloy, set the gap to within a fraction of a millimeter so the rail has somewhere to go in summer heat and doesn't crack apart in winter cold. That tiny gap, the one you've crossed 10,000 times without noticing, is holding the entire system together. That's the thing about engineering. The most important parts are usually the ones nobody sees, the ones nobody thinks about, the ones that only reveal themselves when they're gone. If you enjoyed this video, consider subscribing. And the next time you hear that familiar clickety-clack beneath a train, you'll know exactly why it's there. Thanks for watching. See you in the next one.